Hi, hope you are all fine. In the last lecture, we are discussed about the diode and its properties and characteristics. And we have mentioned that diode has a unidirectional or unilateral conduction properties. This property will enable us to use the diode as a rectifier. So now we will discuss about the rectifiers. Usually when we are starting with the rectifier, a rectifier is a circuit that converts AC signal into a DC signal. That is, we a circuit that AC means it is having a frequency, a time varying signal, and DC means the frequency is there is no time variation of this signal. That is, there is a positive and negative signal in an AC, but the rectifier or the DC will not have the negative part, only positive will be there. So usually when we are discussing about the rectifier, we can have two types of rectifiers: half wave rectifier and a full wave rectifier. First of all, we will discuss about the half-wave rectifier, and remember that this half-wave rectifier also is also not there in the curriculum. But before, in order to understand the full-wave rectifier and its advantages, we should know all these basic things. So that's why we are starting with from the basic itself. So half-wave rectifier means this is the circuit diagram of a half-wave rectifier. Usually this is a step-down transformer. Usually we will have 230 volt AC. So in order to have a practical circuit, we have to step it down. So to step down, we will use a transformer. Usually the in laboratory we will have a step down transformer with output voltages from minus 12 to plus 12 or minus 6 to plus 6. Center tap is it is if it is. So this is a secondary. So from here this secondary of the transformer, it is connected a diode like this, and to it is then connected to a load resistance in series. Now what happens when the power is switched on or when IAC is applied to the primary of the circuit? The transformer will step down the voltage, and the AC signal step down, and AC signal will start to flow through the diode. During the positive half cycle of the diode, that means this end is positive and this end is negative, this diode becomes forward biased because the signal positive and the diode P are the same, are connected together. So this diode become forward biased, and we will have the same, it will pass the output voltage. So if it is ideal, it will pass the entire input signal positive half cycle of the input signal, and we will have a output like this. Now during the negative half cycle, that is when this half cycle reaches here, the diode become reverse biased, so the diode does not conduct at all. So there is no voltage across the load resistance RL. There is no current flowing through the load resistance RL, so there is no voltage across the load resistance RL. So the voltage is zero during the negative half cycle. Now the next positive half cycle comes. So this positive half cycle comes. So the diode again become positive, forward biased. So the we will get an output voltage same as that of the input voltage. Now during the negative half cycle, there is no output voltage since the diode become reverse biased, and this cycle repeats again and again. So the output will be like this. This is the output voltage, and this output will be a pulsating DC. So that is the operation of a half wave rectifier. So only positive half cycles we will get the positive half cycles. There is no negative half cycles in the output. So there is a, we can say that there is a DC, but this is a pulsating DC, not exact DC. It varies from 0 to positive maximum, then to 0, then to again 0, positive maximum, then to 0. But there is no negative half cycle, so it cannot be considered as an AC. But it is not a pure DC. If it is a pure DC, we should not have this variation of 0 to maximum. It is a pulsating, we call it as a pulsating DC. So the output of a half wave rectifier is a pulsating DC. And now another important thing is that if you consider this is the input signal, it is having, suppose it is having a period of 360 degrees. It is varying like this. So this is the output. 0 to 180 degree we will have a signal. From 180 degree to 360 degree there is no signal. That means during the negative half cycle there is no output. Then it starts to repeat again. So the period means the time in which the cycle repeats itself. So this is the period, and a reciprocal of the period is called the frequency. So the this is the frequency of the signal, input AC signal, and the signal output signal repeats again with the same frequency. It takes same time period because this is the actual form of the output signal. A positive half cycle and a zero, a positive half cycle and a zero is the output of the rectifier, half wave rectifier. So this is the frequency again. So output and input frequencies are same for a half wave rectifier. That is very important. There is no reduction in the frequency. If it is it makes a DC signal, the frequency must be reduced. Sorry, the frequency has to be increased. So but there is no change in the frequency. The input and output frequencies of the half wave rectifier are the same. Now let's see what are the disadvantages of a half wave rectifier. That we have seen that the pulsating current in the load contain alternating component whose basic frequency is equal to the supply frequency. Supply means the input frequency. The output and input have the same frequency. And another thing is that the AC supply delivers power only half the time, therefore the output is low. During the other half, that is during the negative half cycle, there is no power is delivered, so we can have only the output is low, output power is low. Now another important thing regarding the rectifier is the rectifier efficiency. The efficiency of any device is defined as the ratio of whatever we are getting to the whatever we are giving. So here we are getting is a DC, and we are giving is AC. So the efficiency of a rectifier can be defined as the ratio of the DC output power to the input AC power. DC output power to the AC input AC power is the rectifier efficiency. This definition is valid for full wave rectifier also. And now we want to find the DC output power. Power is nothing but we know that current into voltage, or I square into R, and this is DC output power and the AC input power. If you come to the input AC power, if you comes to the input AC power, this input is a AC, so we have to consider the RMS value. So it is IRMS square into this input has to flow through the diode and RL. So diode will have a forward resistance RF, and it is has to flow through the load also, so it is RL. So IRMS square into RF plus RL is the expression for the input AC power. The DC output power, the DC pulsating DC has to pass through only through the load resistance. So IDC square into RL is the expression for the DC output power. Now for the half wave rectifier, the value of IRMS is Im by 2. That Im is the maximum current through the diode, or max Im is the peak value of the current, and IRMS value is given by Im by 2 and IDC is given by Im by 5. We will see in the next slide, we will see the derivation of these two expressions. And full wave rectifier will have different expression for IRMS and IDC, but the way of doing the thing is the same. So now by substituting the values of IRMS and IDC in the above expression, and if we take this RF is the forward resistance and RL is the load resistance, if the forward resistance of the diode is very much less than the load resistance, then we can neglect this RF. So we can see that if we substitute it here, the efficiency is found to be 40.6 percentage. So for a half wave rectifier, the efficiency is 40.6 percentage. Now let's see what is the derivation of this IDC and IRMS. IDC means the average value of the current. The general formula to find any average is this one: integral 0 to t, that is integral from 0 to the period t, I dt. I is the instantaneous value divided by integral 0 to t dt is the general formula to find the average of any quantity. So here it is current, so we are taking it as small I, and if we consume that t is the period of the signal, and for a half wave rectifier, if we consider DC output is shown like this, it is having a 0, then it reaches a maximum value. This value is called Im, and then it becomes 0, then it continues until it appears the next positive up cycle. So 0 to t is the period of a rectifier output for an half wave rectifier. So we can say that I is the instantaneous value of current, which is equal to Im sine omega t up to, this is a sine wave, 0 to t by 2. So 0 less than t by 2, this I is Im sine omega t, and it is then from t by 2 to t, that is from t by 2 to t, it is 0, I is 0. So IDC, if we substitute it in the above expression, IDC equal to 1 by t into integral 0 to t by 2 Im sin omega t dt plus t by 2 t 0 dt, because it is 0 for the range t by 2 to t. So it becomes, this Im is a constant, you can take it outside, so Im by t, and this quantity goes to 0. So what remains is 0 to t by 2 sine omega t dt. Sine, the integral of sine is minus cos omega t by omega from the limit 0 to t by 2. So now omega, we know that it is 2 by t, this is omega 2 pi by t. So I'm substituting it here. So Im is by t into 2 pi by t, and I am substituting the limits. It is minus cos omega t by 2. Instead of small t, we are substituting this upper limit, that is t by 2 here. Then minus, so those two minus become plus, cos 0. And of course, if you substitute omega is equal to 2 pi by t here again, so it becomes t by 2 and t by 2 will cancel. What remains is minus cos pi. minus cos pi is minus 1, so minus 1 into minus 1 is plus 1, 1 plus cos 0 is again 1, so 1 plus 1 is 2, so Im by dt will cancel here, Im by 2 pi into 2, so 2 will cancel, IDC is obtained as Im by pi. This is for half wave rectifier. If it is for full wave rectifier, you can see that the here is also having a positive half cycle, so the period is not t but it is t by 2. So if you substitute that expression, you can see that IDC will obtained as 2 Im by pi for a full wave rectifier. And similarly, the IRMS is the root mean square of I. So we have to take first the square, then take its mean and take the square root of it. So here this is the, I am squaring I square, then I am taking the average 1 by t, then taking the square root of it. So here again I am going to substitute those values for I, 1 by t into integral 0 to t by 2. For t by 2, we are having I is equal to Im sin omega t. So Im square sin square omega t dt plus again from 0, t by 2 to t it is 0. So 0 dt all raised to half. Here Im square is constant. You can take it outside. Im square by t. Then we will have integral 0 to t by 2 sin square omega t dt. Sin square, in order to integrate it, I am making a substitution that sin square omega t is equal to 1 minus cos 2 omega t by 2. So 1 minus sin square theta is 1 minus cos 2 theta by 2. So that 2 I am taking to here. So what remains is 1 minus cos 2 omega t dt all raised to half. Now I am going to integrate it. So Im square by 2t, integral of 1 dt is t minus cos 2 omega t is sin 2 omega t by 2 omega, and integration limits are from 0 to t by 2. So Im square by 2t, and here I am applying the upper limit t by 2, and if I am applying the upper limit here for small t, it is t by 2, 2 get cancelled, omega into t, omega is 2 pi by t, 2 pi by t into t is 2 pi, so sine 2 pi is 0. So when I am applying upper limit, I will get t by 2 minus 0. When I am applying the lower limit for t, I am putting 0, so it becomes 0, and here when I am putting it is 0, sine 0 is again 0. So what remains is t by 2 when I am applying the integration limit to these values. So what remains is Im square by 2t into t by 2. So t will cancel. So I will have Im square by 4 all raised to 1 by 2. So Im square by 4 all raised to 1 by 2 is Im by 2. So the IRMS value is Im by 2. Now this is the case for a half wave rectifier. Now for the full wave rectifier, this value, the period you have IRMS, you have to take it from 0 to t by 2. The period is t by 2, and if you substitute it here and do the same calculation, you can see that for a full wave rectifier, IRMS is equal to IRMS is equal to Im by root 2.